Okay, we've got a question with moduluses in it. We want to solve this equation, but this is one occasion where an algebraic solution of this will look a little bit odd, and it gives us a very strong hint that they want us to sketch the graph of that and that to solve the equation. So the method we've done for sketching these graphs is the point of v method. So let's see how that works. For y equals modulus of x minus 1, okay, the point of the v is going to be when the thing inside the modulus is 0, so x is 0, and if I make x equal 0, then modulus of 0 minus 1, y is going to equal minus 1, so the point of the v is at 0, minus 1. And this is also the y-intercept, because taking x is 0 is how I find the y-intercept. So the point of the v method doesn't work particularly well here. I know I've got a v, I know the point of the v is at 0, minus 1, and so I can kind of guess which way up the v is going to be. But the hint given in the question is to actually think about transformations. So thinking about going from modulus of x, which we know is a v with the point at the origin, which is the normal way up. The minus 1 outside just shifts it by 1. It's outside, so it shifts it by 1 vertically down. So the first graph, the f of x graph, looks like this. So this is y equals f of x. And on the same axis, I need to draw the graph of the other one, y equals g of x, where g is x plus 1. Once again, I could use the point of the v method. So what makes the inside of the modulus 0? So for the point of the v for the g of x, I need to think about x plus 1, the inside of the modulus of g of x, being 0. So x plus 1 equals 0, and that equals 0, and that gives me an x value of minus 1. And y is the modulus of x plus 1, which is 0 at that point, so y will equal 0. So this is a v with its point at minus 1, 0, change colour, so that's here, okay. And for g of x, I can get the y-intercept, okay, the y-intercept is when x is 0, so x equals 0 implies that. Modulus of 0 plus 1 is the modulus of 1, so y is 1, so it has a y-intercept of 1. So g of x is a v-shaped graph with a y-intercept of 1, and both of them have this x-intercept at minus 1. Okay, g of x I could get by transforming the basic modulus graph. This is a plus 1 inside, which is a translation of 1 unit, and because it's inside, it's horizontal, it's 1 unit in the negative direction. So now I've got the two graphs sketched, I can just write down the solution to this equation. Okay, so this equation is saying, when does modulus of x minus 1 agree with modulus of x plus 1? When is the red graph the same as the green graph? And I can see that for all of the values here, this is why it's a bit odd algebraically, all of these values of both graphs from minus 1 agree. So all values of x less than or equal to minus 1, so the solution is all x less than or equal to minus 1. So we're starting with an equation, but it turns out that the solution is a whole set of values, okay? All right, I said the algebraic solution would be a bit odd, and I've given myself, you may not have this space in your booklet, I've given a bit of space here to show you how we could try and solve this kind of equation algebraically, and in the next batch of examples we're going to be doing this. So what I need to think about is what modulus can do. So modulus of x, okay, could end up being x because the modulus does nothing, or it could be that it's the modulus of x, or sorry, the modulus of x could make the x into a minus x. And in fact, that's what you did when you wrote the equation of each branch of the graph. So if I do that for this one, here I've got the modulus of x minus 1. Well, if the modulus does nothing, I'm going to get this branch, sorry, which one am I on? I'm on the green one. Okay, I'm on f of x. So if the modulus does nothing, this is just x minus 1. So this graph here is y equals x minus 1. Okay, but the other side of this graph is when the modulus here does do something, in which case I've got y equals minus x minus 1. Okay, because the modulus changes the x to a minus x. Okay, now with the red graph I can do the same thing. So for the red graph, okay, if the modulus does nothing, I get this bit, which is y equals x plus 1. But on the other side, if the modulus does something, it makes everything negative. So this side of the red graph is y equals minus x minus 1. So that means I've got two equations for each graph, and these are I can see exactly why I get all values of x less than or equal to minus 1, because for those values of x, the two equations, y equals minus x minus 1, are the same for both. So these two equations both apply when I'm on the left half of each graph, okay? But to be on the left half of the red graph, I need to be minus 1 or less, because here, between minus 1 and 0, I'm on the right half of the red graph. And I can see that the right-hand sides, this one and this one, these never agree. So my only solutions are going to be when x is less than or equal to minus 1. Okay, so we'll see that idea of putting in one version where the modulus does nothing and another version where the modulus does something. We'll see that to good effect in some of the later questions on solving modulus equations a couple of pages on.